Okay, so our next speaker is Partha Sarathi Ghosh from Presidency University, Kolkata, and he will be speaking on stability of the Haagerup property under graph products. Over to you, Partha.
Okay, so first of all, thank you, Shomoda and other organizers for giving me this opportunity. Okay, so today I am going to talk about the stability of Haagerup property under graph products. So we are now going to the slides. So basically, this is our overview. I will firstly talk about amenability, then some slides will follow up for Haagerup property. Then I will define what is a graph product, and then we will discuss our main result. Okay, so what is amenable group? So amenability, this property was first introduced by von Neumann while he was studying the Banach-Tarski paradox in 1929. So basically, definition of a amenable group is okay. So whenever I am saying in the slide a group, so I always assume that G is a finitely generated group. So a group is amenable if it has a G invariant state on L infinity G. So L infinity G is the collection of all bounded functions on the group, and the group G acts on L infinity as follows. That is, it is something like convolve with small g. So small g acting on F. This function acting on the element T will give us the value F acting on G inverse T. So G invariant state, a state on the L infinity G is basically a functional which takes value 1 on the constant function 1. So a group is amenable if the state satisfies this G invariantness property. And it has been shown that any finite groups, abelian groups, solvable groups, they are all satisfy this amenability property. But non-example would be a free group generated by a free group on two generators. It is not amenable because if you assume that it is amenable, so here you can see on the left hand side, I draw the Kelly graph of the free group, and I can partition the free group into four components. That is A plus, the words starting with A, the A minus part, that is the word starts with negative powers of A, B plus, the word starts with B, and B minus, that is the word starts with negative powers of B. And so if you assume that there is a group invariant state on L infinity G, then you can have that this this equality, that mu acting on the characteristic function on F2 will give you 1, but the characteristic function on F2 will have a decomposition like this. And since we assume that the state is group invariant, so we will have this part that mu of A inverse acting on the characteristic function on A plus, that will be equals to the part mu of chi of F2, right? Therefore, we will have this type of contradiction. Therefore, a free group, it is not amenable, and any group which contains a free group as a subgroup, that will also not be amenable group. So another definition of amenability can be thought of that there exists a sequence of positive definite maps from the groups such that from the group to C such that the sequence converges to one point where that is mu n acting on the value mu n small g, it will converges to 1, and the support of each function phi n will be finite. So why I am telling this? Because we will now see that since okay, before going into the details, I want to say something about positive definite map. So what is a positive definite map? So if we are given a map from a group to C, we will say that it is positive definite. Just look at the second characterization. I will say the second characterization will be our definition of a positive definite map. That is, that map can be written as this type of inner product, where pi is a unitary representation of the group G into some Hilbert space. So if you can write phi as this inner product, we will say that phi is positive definite. Similarly, there is a term that when a map is conditionally negative definite. So given a here I am whenever I say that a function is conditionally negative definite, I will always assume that the function is symmetric. That is, the value on g and the value on g inverse, they are always same. So a function is conditionally negative definite if I can say that this is the definition: the existence of a Hilbert space and a map from the group to that Hilbert space, which satisfies this equation that whenever you whatever elements you take gi and gj from the group, the value on the element gj inverse gi will be like this, the difference of the vector norm square. Okay, so I am giving the I had given the definition of amenable groups in terms of this sequence of positive definite maps. Though free groups are not amenable, Haagerup in 1978 showed that on the free group you can have a sequence of positive definite functions which converges to one pointwise, but instead of finitely supported functions, you will have a sequence of functions which consist of vanishing at infinity type of functions. So here this phi and g goes to infinity as norm g goes to infinity. Norm g means the word length of the group. Okay, so this property later Ackermann and Schoda named this property as Haagerup property. So basically a group is called Haagerup group if we have a sequence of functions on the group G such that the functions are positive definite, converges to one pointwise, and they are vanishing at infinity. So from definition, it is clear that amenable groups have Haagerup property. What Haagerup showed is a bit more that on the free group, if you take the Kelly graph of the free group, that is tree, the distance metric is basically conditionally negative definite. And using Schoenberg's lemma, you can have a different characterization of Haagerup property. That is, a group has the Haagerup property if on that group you can define a proper conditionally negative definite function. So in the later part, whenever we say that a group has Haagerup property, we will always denote this tuple that is written on green, that G phi HR. That is, G has the Haagerup property, phi is the proper conditionally negative definite function, and HR comes from the equivalent characterization for phi being conditionally negative definite. Some examples of Haagerup properties are like free groups, groups acting properly on trees. This is just generalization of free group. Groups acting properly on a finite dimension cat-zero cube complex. And since this paper is all about kind of combination theorem, so there are other algebraic combinations like direct product of Haagerup groups or Haagerup. When you extend a Haagerup group with an amenable quotient, that will also be an Haagerup, and like that. Okay, so I just not want to go into the details of this slide, but just to say that there is something called property T, which is a negation of Haagerup property. So what is the graph product? A graph product is kind of you are given some groups, you want to combine them in such a way that you obtain a new group. This graph product of groups was first introduced by Green when she studies in, I don't know. Okay, so in a thesis she mentioned that. Uh, so what is a graph product? You have a finite graph gamma, and to each vertex you associate a group GV. And so the definition of the graph product is you just take the free product of all that finite group, finitely many groups, and quotient it by this relation. What this relation says is that whenever you have a edge in the graph between the vertex V and W, you just take the commutator GV and GW. The elements from GV and the elements from GW commutes with each other. This is the graph product of the group, and this is denoted by G gamma. So from this picture, it is clear that whenever the graph is totally disconnected, the G gamma will be a free product, and whenever the graph is complete, you will have the direct product of the groups. Okay, so basically this graph product is interpolation between free product and direct product. In the free product situation, every element has a well-defined normal form, and this normal form here, the presence of that commutating relation prevents that. So here you can say that in the graph product situation, you also have a something called reduced form. So what is a reduced form? So any element small g from the group can be written as this product, that is G1 to Gm, where each of the element Gi will come from some vertex group. And there is this kind of shuffling whenever you have edge between the vertex Vi and Vi plus 1, you have this kind of shuffling in the product form. So whenever you have this kind of product form, you can perform three types of operation. Number one is shuffle. After shuffling, if you get identity in any place, you will drop it. And if there is some GI and some consecutive two elements come from the same vertex group, you will just simply multiply it. So like that product form will be called reduced. If you apply any number of times the above operations, it will not reduce the number of elements in the product form. Then we will say that the product form is reduced. But the presence of that commutating relation prevents this reduced form to be unique. Though it is not unique, you can see that the collection of elements in a reduced form. So if you take a G and if you can write a reduced form like G1, G2 times Gm, then this M is unique here. Therefore, you can define a length function that is called a reduced length on this G gamma. So what we will be proving today is suppose you take a finite graph and all the GVs associated to each vertex of the graph have the Haagerup property, then this graph product has the Haagerup property. So on the our target will be to construct a conditionally negative definite function on the graph product G gamma. So before going into the details, I just want to mention some terminology, that is LKV. So if V is a vertex of the graph gamma, then LKV, that is the link of V, that is all the vertex which are adjacent to V. STV, that is star V, it is link V along with V itself. And by STV, we just mean the maximal subgraph of gamma with the vertex at that link and the V. So whenever we mention that GSTV, I just want to say that GSTV is the graph product over the subgraph STV, star V. STV stands for star V. And T will denote this coset-like structure. So you take all the cosets of G star V's running over V in G gamma, and it is just for terminology purpose. The purpose will be clear after some slides. And you form a new Hilbert space, which is direct sum over the vector space, direct sum over this capital T's of HT. So whenever this T is a coset of some G star Vi, we will take HT by HVI. So now we want to define a function on the graph product such that it is conditionally negative definite. So remember that when I say that a function is conditionally negative definite, remember the equivalent criteria, that it will be written as some Rg minus Rh norm square. Just let me go back here. Yeah, right. So this is the formula. So my target is to form this right hand side equation. Okay, so now the definition of the function on the graph product is like that. Take a small g, an element from the graph product. Take one of its reduced form, that is G1, G2, Gm will look like that. where is gi coming from some vertex group, then you will just split you will just apply the RVIs, that is the map coming from the vertex group, RVIs on the GIs portion. And here in the green, the small, it is written that G1, G2, GI minus 1 of GSTI. This is basically mentions the position of the vector. So the first claim is that this map is well defined. Why to check that? Because you know that this reduced form is not unique, so you can have a shuffling at the ith position. So if suppose that vi and vi plus 1, there is an edge in the group, so in the reduced form there is this commutating relation, that is g can looks like this g1 to gm, and this is g1 g2 dot 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 gi minus 1 times there is a commutate, that gi plus 1 times gi to gm. So since this relation is present there, so the reduced form is not unique, so we have to check that r is whether well defined or not. But you can easily see that from the equations written at the uh, written below there, that the position vectors, so the position of the vectors will be same even if we commute the element gi with gi plus 1. Since the position remains same, so the vector r gamma is well defined. Now you can see that this kernel thing, if you can define a kernel on this graph product with respect to this equation, that g comma h, this pair goes to the value r gamma g minus r gamma h norm square. This is the kernel function on the graph product. So you can easily verify that this kernel is group invariant. By group invariant, what I mean to say is that if you hit the argument of the kernel by any group element, the value will not change. So this verification is very easy. You can just visualize this by seeing that whenever you hit some G and H pair by an element Q, you are not doing anything but just writing the elements R gamma UG. You are writing some elements in terms of U in the front of R gamma G, and you are doing the same for R gamma H. And from this subtraction, they will get cancelled, so the value will not be changed. Since this kernel will remain group invariant, so we can define the conditionally negative definite function on the group via this relation. That is basically phi tilde g will take value k of g comma identity. But so at this point of time, we have a function phi tilde on the group on the graph product of the group, but it is conditionally negative definite, but we don't know that whether it is a proper function or not, because you can see that in the previous where we have defined r gamma. So suppose you have things like that, that small g will looks like some g1 g2 g1 g2 g1 g2, this type of expression. Reduced form of G has this type of expression where suppose there is no edge between the V1's vertex and the second vertex, V2's vertex. So there will not be any commuting element, but this RV1 of the element G1 can take value 0. RV2 applied on G2, it it can also take value 0. So the R gamma position, R gamma on that G element can take value 0 as a whole, 0 vector. Therefore, the kernel, if I define like that, that kernel will not be a proper map. Therefore, for making this phi tilde a proper, we need some structure from the graph product. That is basically the cat0 structure of the graph product. So I just want to mention that on the graph product, we have a wall structure. So having a wall structure gives us a well-defined cat0 cube complex on which the group can act. And this result was due to Chatterjee and Niblo. So what is a wall structure? Wall structure is basically you have a space and you just partition it with respect to two subsets. So in the case of graph product, the walls are defined like this, that whenever you take a vertex V, you define WV to be the set of all words from the graph product, which starts with which has a reduced form, which starts with an element from G sub V. So this will define a wall structure, and having a wall structure will give us a cat0 cube complex structure, and from these two relation and the group will act on the cat0 cube complex such that it will satisfy this equation, that the distance in the cat0 cube complex will satisfy this relation, that is 2 times H inverse G sub R, that is the reduced length of H inverse G. So this relation says a lot about the reduced length function. It says that the reduced length function will imitate the properties from the metric of the cat0 cube complex. And Niblo and Reeves sometimes back prove that the metric on the cat0 cube complex is conditionally negative definite. Therefore, we have that this map, that reduced length map on the graph product. This map is conditionally negative definite function. So just we now modify our phi tilde. So previously, remember, we have defined our phi tilde like this, that is norm of r gamma g minus r gamma h norm square. So we modify it by just adding the reduced length function. So our main function from the graph product g gamma to r will be phi gamma will be defined as this LR on small g plus phi tilde on small g. And it is a conditionally negative definite function because it is a sum of two conditional negative definite functions. And the existence of this and the presence of this LR function LR function tells us that this phi gamma will be a proper map. So on the graph product, we have a proper and conditionally negative definite function. Therefore, we can say that this group G gamma has the Haagerup property. Yes, and just to mention, it was first proved by Antolin and Desin, but they never published it. Doing some work, we just obtained a very different proof than them, and recently it has been published. These are some references. Thank you. Any questions?
Yeah. Thank you, Partho, for the very nice talk. Any questions from the audience?
Sumada.
All right. So if there is no question, yeah, Rakesh, any question? No. Okay.
All right.
Let us thank the speaker. Thank you very much.
Yeah. Okay. And once again, thank you.